Welcome to my class on steady state heat transfer. In the previous class, we have formulated the expression for steady state heat transfer through a composite word. In this class, we will extend that idea to include the convection heat transfer on the inside and outside surface of the wall. We already seen the heat conduction through a composite wall when inside and outside surface temperatures are known. So only two conduction resistance were involved, the conduction resistance through the first layer and conduction resistance through the second layer. So you can find out the heat transfer like T1 minus T3 divided by L1 by AK1 plus L2 by AK2. Let us consider a composite wall of two layers with the thickness L1 and L2, and let us take the material properties as K1 and K2. Now the temperatures inside fluid temperature is Ti, and surface temperature here is T1, and interior surface temperature let us take as T2, and outer surface temperature T3, and let us denote T0 as the outside fluid temperature. And inside and outside heat transfer coefficients are Hi and H0. That is for heat transfer coefficient from fluid to surface, and again from the surface to fluid the heat transfer coefficient is H0. Thermal conductivities we will take K1 and K2. In the previous class, we have studied the conduction through a composite wall. So we have not considered the convection here on the inner surface or convection on the outer surface. Directly T1 and T3 were given, the wall temperatures were given. In that case, the heat conduction through these two layers were involved, and we could calculate the heat transfer Q as T1 minus T3 divided by L1 by AK1, that is thermal resistance of this layer, plus L2 by AK2. Okay. So the temperature difference divided by summation of the resistance of both the layers will give the heat transfer in that case. But now we are given the inside and outside fluid temperatures, and convection heat transfer coefficients are given on either side. In that case, let us find out the heat transfer through this composite wall. Now we know that convection heat transfer, as per Newton's law of cooling, convection heat transfer is, you can rearrange the equation and write in this form. Heat transfer is Ti minus T1, temperature difference divided by convection resistance. The actual equation is Q is equal to Ha into delta T, that is H is Hi, Hia into delta T is Ti minus T1. So Ha is taken down, so written as 1 by Ha. Here in this case it's Hia, 1 by Hia. So Q, heat transfer, we can write it as Ti minus T1 divided by 1 by Hia. That is a heat that flows from inside fluid, the fluid present here, to the surface. The heat transfer is given by this expression. Now, as all of you are aware, in steady state conduction through the composite layer, the heat flowing from the fluid to the surface, and heat conducted through the first layer, and heat conducted through the second layer, and the heat flowing from this outer layer to the fluid, all these should be equal. So whatever heat is flowing here, same should be conducted through this. At the same rate, it should be conducted through the second layer, and again should be convected out at the same rate to the outside fluid. Then only steady state will be attained. If in the steady state condition, when all the temperatures are constant, when it attains steady state, all these heat transfer will be constant. Initially, when it is exposed to some fluid temperature, might be an unsteady state. Okay, it will be unsteady state, and after a certain period of time, it will attain steady state. In the steady state condition, heat transfer through all these layers and through the fluid, all this will be constant. Now let us consider the heat flow conduction through the first layer. The conduction through the first layer you can find out as T1 minus T2 divided by thermal resistance of that layer, that is L1 by AK1. So all of you are aware of this, T1 minus T2 divided by conduction resistance of that layer. Similarly, for the second layer also you can write T2 minus T3 divided by L2 by AK2. That is heat conducted through the second layer, the rate of heat conduction through the second layer. And again, now we need to find out the heat convected out from the outer surface to the fluid. So you have to apply Newton's law of cooling. And there the equation is HA into delta T, but I am taking HA down, and H is, in this case, it's H naught, and temperature difference is T3 minus T naught. So T3 minus T naught divided by 1 by H naught A is the heat convected from the outer surface to the fluid. All these heat transfers are equal. So whatever I have written 4 equations now, heat convected from the fluid to the surface, heat conducted through the first layer, heat conducted through the second layer, and heat convected from the outer surface to the fluid. All these are equal, and you can also rearrange these by just cross multiplying. Okay, you can find out the temperature difference as Q into L2 by AK2. Similarly, from the first expression here in the previous, in this slide, no, Ti minus T1, Q into 1 by HI A. Similarly, T1 minus T2, Q into L1 by AK1. So all these equations you can write in terms of temperature difference that I have written here. Ti minus T1 is Q into 1 by HIA, and T1 minus T2 is equal to Q into L1 by AK1, and again T2 minus T3 is Q into L2 by AK2, and T3 minus T0 is Q into 1 by H0 A. Now all the equations you can add. The purpose is to eliminate all these interface temperatures and get the expression for Q in terms of inside fluid temperature and outside fluid temperature. All these expressions are giving rate of heat transfer, but I want to eliminate the interface temperatures involved. Here in this expression T3 is involved, here expression T2 and T3 are involved. So I just want to eliminate and get the expression in terms of fluid temperatures. Generally the fluid temperatures will be known and other properties will be known. So to eliminate the interface temperatures on these surface temperatures, I am doing this. Now if you add all these, you will get the left hand side Ti minus T1 plus T1 minus T2, okay, plus T2 minus T3 plus T3 minus T0. So this minus T1 plus T1 cancels, minus T2 plus T2 cancels, minus T3 plus T3 cancels. You get Ti minus T0. So that means inside fluid temperature minus outside fluid temperature. So that is equal to, here Q is common, Q into, this is convection resistance, inside bracket is convection resistance, and this is conduction resistance of first layer, this is conduction resistance of second layer, and this is convection resistance on the outer surface. So Q into, add all these resistances. So you get, by adding that, left hand side you are getting Ti minus T0, and right hand side you are getting 1 by HIA plus L1 by AK1 plus L2 by AK2 plus 1 by H0 A. Now if you rearrange, you will get Q is equal to Ti minus T0 divided by 1 by HIA plus L1 by AK1 plus L2 by AK2 plus 1 by H0 A. Now you can represent this in the form of a thermal circuit. So Ti and T0 are the fluid temperatures. In between, whatever resistance are involved, you can write convection resistance for the inner surface, fluid surface layer. This is conduction resistance for the first layer, conduction resistance for the second layer, and convection resistance on the outer surface to the fluid. You can find out the heat transfer directly if you take 2 points Ti minus T0 divided by add all the resistance in between. Then if you are taking Ti and T0, the resistance, all resistance you will get. You have to add all the 4 resistance and divide by that. Ti minus T0 divided by addition of all these resistance. Suppose you are taking Ti and T2. Ti minus T2 divided by only these 2 resistance you should add and divide. So Ti minus T2 divided by 1 by HIA plus L1 by AK1. That will give Q. So similarly any 2 points you can take, and that difference in temperature divided by summation of the resistance in between the 2 points. Suppose you take T1 and T3. T1 minus T3 divided by L1 by AK1 plus L2 by AK2. Or if you take T3 and T0, T3 minus T0, there is only one resistance in between. So T3 minus T0 divided by 1 by H0 A. So this way you can use this thermal circuit and easily you get the heat transfer in terms of different temperatures. So this helps to find out the interface temperatures. Once you get the heat transfer through the composite layer, suppose you require interior surface temperatures. So already heat flow is known. You can use any of these equations, say T2 minus T0 divided by summation of the resistance is Q, and Q is already known. You can find out T2. That way you can use these expressions to find out the interior temperatures. Thank you for watching.